And so we will be using free body diagrams to show the relative magnitude and direction of all the forces acting on an object in a given situation. And now let's try a couple of those out. Let's draw a free body diagram for a book sitting on a tabletop. Now the free body diagram does not have to be a very realistic representation of a book. In fact, a lot of our free body diagrams will look the same, a generalized box. We'll draw in the center of mass, and what we'll do is we'll consider all forces to be acting on the center of mass. And so on this book, we can assume that it's on Earth. We'll have the force of gravity acting on it. And notice that this book is sitting on the tabletop, not accelerating through it, which means there must be some other force acting on the book that is balancing that gravitational force. And the force that supports any object which is sitting on a horizontal surface is known as the normal force. And so in this case, F net would equal Fn plus Fg. And because we're not accelerating, the F net is 0. Fn plus Fg. We'll give these all vector signs. And because of this, we can say that Fn is equal to the negative of Fg, which is to say they're equal in magnitude, but opposite in directions. And so, in the second example, we will draw a rightward force applied to a book and moving it across a desk with a rightward acceleration. So again, here's our desk, and here's our book. Now, before we go anywhere with this, we should remember that, again, this book is going to be subject to gravity. And because it's not accelerating through the desktop, there's also a normal force attached to this. Now, we've got an applied force acting to the right and giving this book a rightward acceleration, which means that this force is unbalanced, or at least a portion of it is. This being the real world, we do have a frictional force. Now, if this book is accelerating to the right, what that means is there must be a net force towards the right, which means that the frictional force is necessarily smaller in this situation than the applied force. Next, we'll draw a free body diagram for the following. A car is coasting to the right and slowing down. And so, again, we'll draw our simplified car, greatly simplified, in fact. And again, imagine this arrow was pointing straight down. We have a force of gravity acting upon it. And again, cars typically don't accelerate through the pavement, so there must be a normal force acting on the car as well. Now, if it's moving to the right and slowing down, that is equivalent to an acceleration to the left. And because it's coasting, that implies that the gas is off. Maybe this car is in neutral. Maybe it's turned off. But there should be no force to the right. Even though it's moving towards the right, it can do that. It can do that without a force to the right. there was a force to the right that got it moving, but in this case, because it's coasting, there's no force to the right. Because it's slowing down, we know that there must be a net force to the left, and in this case, the force that's slowing this down is a frictional force. Now, this is going to be a generalized frictional force. It's not a sliding friction like the book experienced as it slid across the tabletop. This would be the frictional force of the tires deforming on the road. This would be the friction in the bearings. This would be wind resistance as well. And so in this case, because we're not just talking about two surfaces sliding together, this frictional force can't be calculated in the same way as the other ones, as we saw before. So in recognition of that, maybe I won't call it a frictional force. Maybe I'll call it FR for being a retarding force or a slowing force. It doesn't matter particularly what you call this. Now, typically the downward gravitational force is going to be called Fg. Typically, the normal force, which supports an object on a horizontal surface, is going to be called Fn, or the normal. And typically, an applied force is going to be Fa. But even if you don't use those conventions, those ones you probably should, but even if you didn't, you wouldn't be incorrect. These names are kind of arbitrary. And the names are less important than their direction and their magnitudes. And so let's draw a diagram then of a trapeze artist hanging motionless from a bar. In fact, let's draw the diagram for the bar. In this case, in some cases, as we'll see later in the course actually, it can be more useful to draw elongated structures as being long and locating the forces along that structure. So in this case, we have a trapeze bar with a tension force acting upon it upward from either end. And let's assume that this trapeze artist is holding on with two hands, and we'll have the force of the trapeze artist's weight pulling down on the bar. And each of these forces will be half of the weight of the trapeze artist. Next, we'll look at the free body diagram of an egg falling from a tree. And in this case, let's ignore air resistance. And so we have an egg, again, idealized. This is not sitting on a surface, so there won't be a normal force. However, there will be a gravitational force that will cause the egg to accelerate downwards. And in fact, since we're ignoring air resistance, this is all the forces acting on the egg. This is unbalanced, and thus it'll cause an acceleration, which you would expect for something falling from high up. In this example, this is a lot like the egg. We'll draw an idealized, simplified parachutist, and the force of gravity acting downward on that parachutist. And notice that this guy, or girl, is descending at constant velocity. And so there must be something balancing this Fg. The constant velocity means that there's zero acceleration. If there's zero acceleration, remember that F net equals m times acceleration. If acceleration is zero, F net must be equal to zero. That means there must be something balancing this force of gravity. In this case, that is the force of the air resistance acting on the parachute. Maybe we can call this Fp for parachute. Again, in this case, where we have the parachute is descending at constant velocity, there's no acceleration, thus there should be no net force. So what's happened here is this parachutist has reached his terminal velocity. What the parachute does is increases wind resistance, so increases this force, so that it equals Fg at a low enough velocity that the parachutist doesn't get hurt. Air resistance increases with velocity, and so eventually you're going to run into a terminal velocity where the wind resistance, air resistance, is equal to Fg. Now, if you're not carrying a parachute, that terminal velocity happens at way faster than you would like, and when you hit the ground at that velocity, typically you get very injured. When you have a parachute on, that terminal velocity happens much sooner, at a much lower velocity, and thus you can stay safe. In this example, we have a bricklayer standing in the middle of a 3-meter long plank supported on sawhorses at both ends. And so we could certainly draw a diagram of the bricklayer or either of the sawhorses. The more interesting diagram is that for the plank. And so in this case, we'll have two forces acting upward, which are provided by the sawhorses. We can call them F1 and F2. Again, in this case, it doesn't really matter what these names are, as long as you use the same F1 to mean this force throughout your calculations, then you'll be okay. And here you'll have the weight of the bricklayer acting at the halfway point of the plank. In this course, you'll see a lot of things on ramps. And so this diagram becomes decently important. So here, this box is sitting on a 30-degree ramp, which is to say that this angle is 30 degrees. And we can I'm going to draw this rather big because that becomes beneficial later. So here's the center of gravity of this object. And I'm going to draw Fg fairly large, only so that this triangle is complete here. Now, remember that the normal force is going to be perpendicular to the surface of the ramp. So the normal force is going to be like this. I should draw this a little bit larger probably, but this diagram, because of the limitations of space, won't be to scale. So the normal force is going to be there, perpendicular to the ramp. And also, notice that if this box is going to move anywhere, it's going to move either down the ramp in this direction or up the ramp in this direction. And so it doesn't make sense to think of this in terms of the normal x and y coordinates. In fact, it makes more sense to tilt the axes that we deal with by 30 degrees to match the ramp. Because again, the normal force is going to be in this direction, not straight up and down, because any motion of the box is going to be in this direction, not just in the x direction. So it makes more sense to deal with these axes. And so Fn is going to be on that axis, on this y prime axis, but Fg is not. And so whenever we have a vector that is not in line with the axes that we want it to be in line with, what we're going to do is take components. So let's take components of FG. And so components are going to look like this. This is going to be FGY prime. It's the y prime component of the vector FG. Let's also take this component. This is going to be FG x prime. This is the x prime component of the vector FG. Notice that FG, in terms of x prime and y prime, pulls the box into the ramp and also pulls the box down the ramp. This makes sense because, as you've experienced, if you put an object on a ramp, it doesn't just shoot off of the ramp, it stays there, and it doesn't roll up the ramp, it rolls down the ramp. So this does match with what you've noticed in the real world. And so because y prime and x prime are by definition perpendicular to each other, we can make this a right angle triangle too. Now, let's see about calculating FGY prime. Why? Because it's going to be equal to Fn, and we'll also calculate FGX prime because that's the force that's going to pull the box down the ramp. Fn, the reason Fn is important is because Ff, the frictional force, which will be going in this case because it's just sitting on a ramp. The normal tendency of this object would be to slide down the ramp, and thus the frictional force will oppose that tendency. So let's look. In the y prime direction, we've got FGY prime and Fn. Because those are the only two forces acting in the y prime direction, those two are going to be equal to each other. And so Fn should be a little bit longer, it looks like. So I'll do that. So Fn maybe should look like that or so. If it's sitting on this ramp, then it's not accelerating up or down the ramp. It's not accelerating off or into the ramp. That means that FGX prime must be equal to FF. That is to say that FGX prime must be lower or equal to the maximum force of friction that can be generated. The maximum force of friction, remember, is mu, or the coefficient of friction, times Fn. We'll do a lot of practice in this type of problem. So don't worry if this is feeling a little new. We will get to it. But let's first calculate components of Fg. So FGY prime. Before we actually do that, let's figure out what angles we're dealing with here. If this is a 30-degree angle, and this is a 90, then this must be a 60-degree angle. Right there. And because we have two lines intersecting, this angle over here must also be 60 degrees. Now, this angle over here, because it's between the y prime axis, the y prime direction and the ramp itself, which is in the x prime direction, this must be a right angle. And so if this is 60 and this is a right angle, then this angle up here must be 30 degrees. And so, relative to this 30, FGY prime is adjacent to it. And so, FGY prime is going to be equal to FG, which is the hypotenuse of this triangle in question, this triangle here, here, and here, formed by FG and its two components. FGY prime will be equal to FG times the cos of 30 degrees. Let's take a step back and figure out why. Recall that the cos of 30 degrees is equal to the length of the adjacent side divided by the length of the hypotenuse. So in this case, cos 30 equals FGEY, the length of FGY, which is adjacent to 30, divided by the hypotenuse, which is FG. Solving for FGY, multiply both sides by FG. Cancel and cancel. FGY equals FG cos 30. Similarly, for FGX prime, we're going to use the same triangle, but FGX prime is opposite the 30, so we're going to use the sine, and in a similar calculation, FGX prime is going to equal FG sine 30 degrees. There are some homework questions that go along with this. I will post these to Blackboard as well, to relevant pages. So, questions 3.23, 25, 26, 27, 28, those are all worked examples. So you can use the explanations as given in the book. And these 346, 354, 359, 364, 367, and 370 are all non-worked examples. So we can deal with those in class if you have any problems with them. All right, I will see you guys shortly, and good luck with these things, and I hope this has been useful.